Isomerism in coordination chemistry. Coordination compounds also exhibit the two types of isomerisms. That is the structural isomerism and the stereo isomerism. For the structural isomerism, we know that the complex has the same number of atoms, the same number and type of atoms, but different connectivities. For this one, same number of atoms, same number of and types of atoms, but different connectivities. That means if we are looking at structural isomerisms, we are looking at how the ligands and the metal atoms are connected to each other. And now for the stereo isomerisms, this for the complex has the same number and types of atoms, the same number and types of atoms, and the same connectivity, but different arrangement in space. So now, we were looking at the structural isomerisms. Under structural isomerisms, we have ionization isomerisms, hydration isomerisms, ligand or linkage isomerism. And I'm going to explain this very well with examples for you to get it very clearly, so that you'll be able to identify any type of isomerism when you are given coordination complexes. So for the structural isomerisms, I think we have two more left, and I'll be treating them very well. Let's deal with these. Let's deal with 1, 2, 3. Let's deal with this one. We are done. Then we continue with the others. So ionization isomerism. For ionization isomerisms, look at these complexes. Can you see this and this complex and this complex? What do you see? Can you see any difference? Here we have SO4 as a ligand, and here we have SO4 as a counter ion. Mind you, if you have a coordination, for everything that is in the square bracket, make up the coordination sphere. Anything outside the square bracket is a counter ion. So we have counter ion and a ligand exchanging their places. If we have counter ion and a ligand exchanging their places, then we know that the kind of isomerism exhibited is ionization isomerism. So here we have CO bonded to NH3, CO bonded to NH3. We have SO4 and B3 here. And here we have B3 inside. That means SO4 has changed its position with BR. So this means we have ionization isomerisms here. This pair of complexes exhibit ionization isomerism. Let's look at hydration isomerism. For hydration isomerism, is a type of ionization isomerism. But in this case, we have water acting as a ligand, and and in the other case, it is acting as a water of hydration. You see, we have water here as a ligand. We do not have water outside here, but for this complex, we have water inside as a ligand, and we have water here acting as a water of crystallization. So if you see any pair of complexes behaving this way, then the type of isomerism displayed here is hydration isomerism. Hydration isomerism and ionization isomerism are the same, but just that it is hydration when we are talking about water. If we see water acting as a ligand and at the same time acting as a water of crystallization, then we call it hydration isomerism. So let's look at ligand or linkage isomerism. For this one, we have a ligand in a complex. Even if it's not a ligand, even if we have more than one ligand, at least one of the ligands have to point in different ways. Point of attachment of at least one of the ligands has to differ. If you see this, if you look at this complex, NO2, here we have ONO. So in this place, we have N coming first before O. N coming first before O means that it is nitrogen that has donated a lone pair of electrons to form a complex with cobalt. And this place, we have O coming first, showing that it is oxygen, that has donated a lone pair of electrons to form a complex with cobalt. So in this place, the donor atom is nitrogen, and in this complex, the donor atom is oxygen. So if we see ligands behaving in this way, then the type of isomerism displayed here is ligand or linkage isomerism. Let me give you a clue. Anytime you see an ambidentated ligand, then be expecting ligand or linkage isomerism. And the type of ambidentated ligand that we have are the common ones. We have thiocyanate, SC, and thiocyanate. We can have a point, in which sulfur will be forming a complex with a metal atom. And we can also have a point in which nitrogen will be forming a bond with a metal atom. So in this place, we have sulfur as a donor atom, and in this place, we have nitrogen as a donor atom. So if you look at this one, nitro, NO2, nitro, the donor atoms is nitrogen. And if you look at nitrito, ONO, nitrate, the donor atom is oxygen. So anytime you see, this kind of ligand, be possibly looking out for linkage or ligand isomerism mostly. So now let's look at the other two. Okay, for the other two types of the structural isomerism, we have the coordination isomerism and the polymerization isomerism. That means in coordination complexes, the types of structural isomerism that we can get are ionization, hydration, ligand or linkage isomerism. And okay, let's continue with this. So coordination isomerism. For this kind of isomerism, look at this complex very carefully. Look at the pair of complexes here very carefully. This is number one, and this is number two. You will see that from the first pair of complex, you see cobalt here coming first, and here chromium here coming second. We have cobalt forming a complex with ammonia, and here we have chromium forming a complex with cyanide. The second one, we have chromium forming a complex with ammonia, and followed by cobalt forming a complex with cyanide. You could see that from the first pair of complexes, we have cobalt forming a bond with ammonia, forming a complex with ammonia. And from the second one, we have cobalt forming a complex with cyanide. And from the first complex, you can see that chromium, this is where the problem comes from. Look at the metal atoms. They exchange ligands. The metal atom exchange ligands. If exchange ligands. So anytime you see something like this, then possibly, is the complexes are exhibiting coordination isomerism. So changes of ligand between the cationic part and the anionic part of the complex. So I hope this is clear. You can see that we have cobalt here forming with ammonia, but here the two metal atoms that are in this complex are what and what? We have cobalt and chromium. So at the end of the day, cobalt and chromium are going to exchange their places. So where cobalt was, we have chromium to come there. And where chromium is, we have cobalt to come there. So that means at the end of the day, they exchange their ligands. So if you see something like this, then we have coordination isomerism. Look at number two. You can figure this out by yourself. You can see that we have zinc here, copper here, zinc here. If exchange their positions. So you will see that this is clearly coordination isomerism. So the other type, the last type of structural isomerism that is left is polymerization isomerism. I brought this so that you know that we also have something like this. But mostly we look at the ionization, the hydration, the ligand and the linkage, and the coordination isomerism. Those are the most common ones. But for this one, you can also look at, you can also research on it. And it's just simply that it is possible. It's one of the possible isomerism in coordination chemistry, in which the complexes will have the same empirical formula but different molecular weight. So this is just basically what is behind polymerization isomerism. So thank you for watching. Kindly like this video and subscribe to my channel for more. And before we conclude on structural isomerisms and the coordination chemistry, I have an example. I have examples here. I want you to try them and let me see your answers in the comment section. Is you are to identify the kind of isomerisms displays, exhibited in the pair of the following complexes. So treated structural isomerisms and the coordination complexes, like we said earlier, that for coordination complexes they also exhibit the two types of isomerism, that is the structural and then stereo isomerism. And the structural, we said we made mention that for the structural, the complex has the same number and types of atoms but different bond connectivity. But for stereoisomerisms, the complex has the same number and types of atoms, the same connectivity, but different arrangement in space. So now we are going to look at the stereoisomerisms, and we have two types of stereoisomerisms. We have the geometric isomerisms and we have the optical isomerisms. So for the geometric isomerisms, this is subdivided into two. We have the cis and the trans isomerisms. And we also have the Fac and the Merd isomerisms. Sorry, there is a short form for facial isomerisms, and the Merd is a short form for meridional isomerism. So I'm going to break everything down so that you get it very well. So first of all, let's look at the Fac and the Merd isomerisms. If we have complexes that display, let's say that has two ligands, the first ligand, three of the first ligand and three of the second ligand, then the highly possibility that this compound is going to exhibit Fac and Merd isomerism. under geometric isomerisms. So anytime you see complex in this form, that means that we are definitely going to get Fac Merd isomerisms. So let me write this so that anytime you see a complex like this, assuming we have cobalt forming a complex with chlorine, 3 of chlorine, and also with 3 of let's say water. So the highly possible isomerism that this complex can display is the Fac and then Merd isomerism. So let me break this down for better understanding. You can see that we can have cobalt like this, 1, 2, 3, 4. Let's say if this is the solid wedge, this is a dash wedge. There can be a point where we will have all the chlorine ligands at the same place and all the water ligands, the water ligands at the same place, like this, like this. So you can see that the water ligands are facing at the same direction and the chlorine ligands are facing at the same direction. So for this one, we call it the facial. So this is the facial, which is the Fac isomerism. So there can also be a situation where we will have cobalt like this. Let's say this is not solid wedge and this is not dash wedge. There can be a point where we will have chlorine to be at, let's say we have water to be at this side. We can have H2O to be here, H2O like this. And we have chlorine to be here, chlorine to be here, chlorine to be here, and then H2O, to be here. So looking at this, you can see that the group of the ligand, the 3 groups of the ligand, the 2 groups of the ligands are not at the same time, they are not at the same place. They are not facing each other. They are not grouped as compared to this. You can see that here the chlorine, all the chlorine are at one side and all the water ligands are at one side. So this one is the meridional, which is a Merd. So that is it for the Fac and Merd isomerism. So anytime you see a complex that the first ligand is, you have 3 of the first ligand, 3 of the second ligand, then you are definitely going to see Fac and Merd isomerism, which is under geometric isomerisms. So let's look at the cis and trans. For the cis and trans too, just look at this formula. Complexes that are in this form are highly exhibiting cis and trans isomerisms. You could see that we have assuming this is a metal atom, the central atom bonded to 2 of a ligand A and 2 of ligand B. Or we can also have another situation where our central metal is bonded to 4 of ligand A and 2 of ligand B. So a typical example for that is you could see from here we have platinum here, and we have 2 of ammonium here, we have 2 of chlorine here. So this complex is definitely going to exhibit cis and trans isomerism. So let me break this down for better understanding. Cis and trans, because if let's say we have a platinum in the middle, we can have NH3 here, NH3 here, NH3 here. You have a chlorine here, you have a chlorine here. Looking at this, which of these molecule is of higher priority? Chlorine has higher atomic number than that of nitrogen and then hydrogen. So you can see that the higher priority is on chlorine. From this, you can see that the chlorine, which is of higher priority, are grouped at the same side. At the same side. So this is the sixth isomerism. This gives us the sixth. And there can be a point where we have the higher priority, being at the opposite side. So let's say we have platinum where we have chlorine here, and then NH3 here, NH3 here. So mostly complexes of this form exhibit cis and trans isomerisms. You see that you have the central atom bonded to two of a ligand and two of another ligand. So cis and trans isomerism. There can also be a case where we have something like this. Yes, there can be a case where we have something like this. The second type, which is the metal atom bonded to 4 of ligand A and 2 of ligand B. Typical example is this. So we can have our cobalt in the model. This is the general structure of octahedral complex. Let's say this is on the solid void, this is a gas void. So let me draw it all so that we start arranging. So now, so there can be a point where we have chlorine here to be here and here. I mean, we have 2 of chlorine and we have 4 of ammonia. So Na3, 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 Na3. You could say that comparing ammonia to chlorine, the higher priority group is chlorine. Chlorine is found at the opposite side, and this gives us the trans isomer. The trans isomer, trans. Let's say there can also be a point where we have our chlorine, all our chlorine to be like this, and the rest will be Na3, NH3, NH3, NH3. So for something like this, you see that we have the cis isomer here, the cis isomer here. So now let's look at the optical isomers. For the optical isomers, I don't know how to explain this to you, but let me try my best. But anytime you see a complex in which we have a bidentate ligand or three of bidentate ligands, then that means that complex is exhibiting optical isomers. For these isomers, they are non-superimposable. If we arrange them, you are going to see, any line of symmetry. Like if you look at this cis and trans isomers, looking at this trans isomer, you can see a line of symmetry here. You can see we can divide this complex into 2. So for optical isomers, if you arrange them, you are not going to see anything like that generally. So they are non-superimposable mirror images. And mostly, if you have a coordination complex in which the metal atom is bonded to 6 different types of ligands, if that exists, then you definitely going to see optical isomerism. And I think that is for the optical isomers. Anytime you see something like this, you should definitely know that the kind of isomerism you can spot here is optical isomerisms. So thank you for watching, and don't forget to like and subscribe my video and comment